So we've talked about various methods to solve higher order differential equations. In particular, we looked at the method of undetermined coefficients. There we learned how to solve differential equations with constant coefficients that were linear. Okay, so that was an important part, and that included non-homogeneous equations. So we were able to solve those. But of course, we are left with the question of what happens when we have variable coefficients. Okay, we'll still stay in the linear domain, and even though we could find a method to solve differential equations in principle that have variable coefficients, it might not be practical to do so. It might be difficult. And among such difficulties with the method of variation of parameters is that you need to have a known complementary function. Okay, so the associated homogeneous differential equation of a non-homogeneous equation, of course a linear one, the solution to that should be known. And you build the particular solution from the complementary function. Okay, so that's a crucial part, and it limits the amount of differential equations that we could solve to the ones where we at least know how to get a complementary function for. I should also add that while the method of undetermined coefficients had a limitation on the form of the non-homogeneous term in the differential equation, okay, so there was we were only able to take exponentials, cosines, sines, polynomials, and take products and sums of these types of finite products and sums of these types of functions. The variation of parameters in principle does not have that limitation. In this video, we will build the theory behind the variation of parameters, and we will then look at examples. So let's build the theory. We're going to start by looking at using the variation of parameters, or an analog to it, for linear first order differential equations first. Okay, just to kind of start with an easy example and then build to the second order and even generalize to higher order linear differential equations. So consider the linear first order differential equation that you see here. Of course, a1 must not be equal to 0 on the interval we're interested in. And the ai, all the coefficients in g of x should be continuous on I. So we're going to put that in standard form, and we get this. Of course, there was no problem with dividing by a1 because it's never 0. That's an assumption. And let's look at the associated homogeneous equation. Okay, we just set this f of x equal to 0 for the associated homogeneous equation. And, we could solve this by, say, separation of variables. Okay, and we get this complementary solution. Okay, this is just the general complementary solution to the associated homogeneous equation. Okay, the complementary function. And we're going to define y1 to just be this part. Okay, so we're going to ignore the constant and let y1 just be that. And now we're going to make a further assumption. We're going to assume that the particular solution is proportional to y1, where the proportionality is actually a function. Okay, so not like a constant proportionality, but it's a function. We're going to assume this form, in other words, okay, that yp is equal to u1x, y1x, where u1x is a function. So let's take the derivative of yp. We get that from the product rule, and we're going to substitute it into the differential equation that we started with here, so the non-homogeneous one. And when we do, we get this relation. Now, simplifying, factoring out this u1, we get this term here. Well, that's 0. How do we know that's 0? Well, y sub 1 was the solution to the associated homogeneous equation. Okay, so we know that this has to be 0. That's how we found y1. And so we're left with this equation there. This can be integrated with respect to x here, or we should have, to be more proper, used the dummy variable t, okay, t, and then had an x there. But if that's not going to be confused, we could solve for u1, and we'd have to do this integral. And now from our assumption of the form for y particular, that it's equal to y1 u1, we're left with this right here, yielding this for y particular, okay? And then what's our general solution? Well, it's going to be the complementary function plus a particular solution to the differential equation, non-homogeneous one. Here's our complementary function. Here's our particular solution. And this agrees with the methods that we've done before. So the linear equations method that we looked at for first order linear differential equations. Okay? So this process, we're going to take the general outline of what we're doing here, but abstract it to higher dimensions. In particular, we're going to now do this for second order differential equations. So let's start with the linear second order differential equation that you see here, the non-homogeneous one. Of course, a2 does not equal 0 on I, and the coefficients in G are continuous. Okay, that should be continuous there. Okay, we're going to put it in standard form by dividing by a2. Okay, and we get this here where, p of x is just going to be a1 divided by a2 and so on. All right. Well, let's assume that we have our complementary function from the associated homogeneous equation. And if these coefficients were constants, then that's not a big deal. It's pretty easy to solve second order differential equations with constant coefficients. But if it's not, okay, then, well, this is a huge assumption, right? Because sometimes it could get pretty tricky getting the complementary function for that, for a differential equation with variable coefficients, okay? So we're also going to assume that yp, the particular solution, has the form u1 y1 plus u2 y2, where y1 is the first function in the complementary function, y2 is the second, okay, ignoring this constant. So this is an assumption, all right? So we're just assuming that this would work, and we're seeing how far we could get. Of course, this will work for differential equations that respect this form. So differentiating once and then twice, we get this. Okay, now what are we going to do? We're going to plug it into our non-homogeneous equation there. And we're going to factor out some terms, combine some terms. As you can see, this gets really long, okay? But if you follow through the algebra, you'll get a term like this, which we know is 0. Why do we know it's 0? Well, because y1 solves the associated homogeneous equation. y2 does as well, okay? That's part of our assumption. So that's 0. And of course, all of this is equal to f of x, the right-hand side. And we're then going to pull out a derivative, if you will. Okay, you could kind of think about it as factor a derivative from some of these terms here that are left, and we get what you see here. And simplifying that expression, Okay, just combining these terms and simplifying, we get this. And now this provides us, this is a single equation for two functions, u1 and u2. Remember, that's what we're solving for, u1 or u2. Once, both of those. And once we have those, well, we have our particular solution. Two functions, one equation, that's not good. So we're going to further assume another relation that will simplify this equation. We're going to further assume this, okay? We're going to assume this relation right here. It's just an additional assumption. It's an additional constraint that we put to make the computation easier, okay? And once we do that, this is 0, and that's 0. And we're left with this relation here, which simplifies to that. Okay? And so we have now these two equations that will give us u1 and u2. Okay? So we could take equation 2, multiply by y1, and subtract y1 prime from 1, and we get this. And this provides us with an equation for u2. We do something similar and get an equation for u sub 1. Okay? On the right hand side, you see nothing but known inputs. And on the left hand side is the unknowns. And so we could then integrate those to get u2 and u1. So here's a summary of the method of variation of parameters for linear second order differential equations. Consider the linear second order differential equation in standard form, where p, q, f are continuous on the interval I, and suppose that the associated homogeneous differential equation is there and has complementary function that you see there. Then a particular solution in this form here, this here is the particular solution where u1 and u2 satisfy these two equations, and when solving these two equations, we get these formulas for u1 and u2. Okay? And note here that the denominator in both of these is just our friend, the Wronskian. Okay, so you just take the determinant of that. That's the denominator. And we invent these two terms, W1 and W2. Okay, W1 is the Wronskian with the first column being substituted into this 0f, okay, the non-homogeneous term. And W2 is that same column substituted for the second column, okay? So that's our method of variation of parameters for linear second order differential equations. Someone might be concerned that the denominator would be 0, but we know that the complementary function has two linearly independent functions, y1 and y2, and so the Wronskian will not be 0 from the previous theorem that we looked at. And finally, it may be concerning that we're making this assumption that the particular solution has this form, and we make the additional assumption that we have this relation here, okay, to simplify that equation. But at the end of the day, this works for many differential equations, and so we adopt it, especially in our course that's focused more on computation.